Hey calculus friends, welcome to section 4.7 on optimization. Optimization is applications of integration. Here are your guidelines. I actually have typed these up and I put them in, I'm not sure where I'm going to put them. I don't know, look for them on Blackboard. I'll have a link to them. I will put it in your email tonight. When I send out your Sunday night email, I will tell you where I put these guys. I'm not sure the best place to put them. So anyway, when we do optimization problems, this is going to be word problems that involve differentiation. Here's the guidelines. You don't have to write this all down, but I will go through it. We want to introduce our variables, and if we can draw a picture, draw a picture. Pictures are often super helpful. We have to decide what we are going to maximize and look for relationships between variables. And we want to write a formula involving the variable the quantity that wants to be maximized in relationship to the other variables. Sometimes our quantity that wants to be maximized is a function of several variables. We will be given enough information to rewrite the equation as a function of one variable. This will all make more sense when we see this. And then we're going to differentiate and find the maximum or minimum value of the variable of interest. So that being said, let's just jump right into a problem. Now these problems, also I have 4 problems for you. When you click on this link and with all these guidelines, and the second page will be the 4 problems listed out, so you don't have to write down all the problems. All right, so our first problem here, I know this is going to be hard to read, but it's what I had here at home. So this problem says we have a farmer with 4,000 feet of fencing, and he wants to enclose a plot and it borders a river. The farmer wants to put the fence on 3 sides. He doesn't need fence along the river, but he wants to maximize the area in which he's going to use for the whatever purpose. All right, so let's see what's going on here. I like to draw a picture. Here I have water. And then I'm going to have my 3 sides of my fence, right? So it's a rectangular fence. Now remember, squares are also rectangles. Not all rectangles are squares, but all squares are rectangles. This is a rectangular fence. So there's no guarantee that the width and the length are going to be the same. So I'm going to call the width X and the length Y. And what we want to maximize is the area. In the area, and usually I use letters that correspond to what we're talking about to make it easier. So the area of this plot is going to be the length times the width. So here's an example where our area is a function of 2 variables. We want to bring it down to a function of 1 variable. So we want to maximize the area. Now, we're also, obviously, if we had unlimited fence, we could make an enclosure with infinite area, but that's not the case. We only have 4,000 feet of fence here. So we identify what we call a constraint. So a constraint in max-min problems is something like telling us we only have a certain amount of fencing that we can use. There's a constraint here because obviously if we could have unlimited fencing, we didn't have this restriction, then the pen could be as large as we wanted it to be or as much area as he had on his farm. So the constraint is we have 4,000 meters of fencing. So the sum of these 3 sides can be no bigger than 4,000, and common sense tells us that in order to get the maximum size of a pen, we would have to use all 4,000 feet. So I'm just going to combine this, and I'm going to rewrite this as 2x plus y equals 4,000. So this is what we want to maximize. A, it's a function of 2 variables. Here's our constraint. Now, we're going to use our constraint to rewrite the area in terms of 1 variable. So notice using the constraint, we're going to take, whoops, don't change the numbers, 2x plus y equals 4,000. We're going to take our constraint equation and we're going to solve for one of the variables. And you can solve for either one. I typically solve for the one that's easier to solve for. So in other words, I'm going to just solve this for y by subtracting 2x. I could solve for x by subtracting y and divided by 2, but I'd introduce fractions, which isn't terrible, but I'm just going to avoid this. So if we have 4,000 feet of fence, the length is going to be 4,000 minus the 2 sides. So now what I'm going to do is take this and stick it up here in for y. So now the function we want to maximize is the width times the length, which is 4,000 minus 2x. So now the area is expressed just in terms of the width of the fence. So I'm going to distribute and rewrite this as, because taking the derivative of a polynomial expression is better and easier than taking the derivative of a product. It's just easier. So the area is now a function of just the width. So to find the maximum area, we want to maximize this function. If we think ahead a little bit, we can see that this is a quadratic equation with a negative leading coefficient. So if we were to graph it, it would look like this, an upside down parabola. So it definitely has a maximum value. But we have to find the value of that maximum value. So to maximize this problem, we're going to take the derivative. Now this is not a related rate problem. The fence is not changing with respect to time. So we're literally just going to differentiate each side. Area is a function of x. So the derivative of the area is the derivative of 4,000x minus 2x squared, or 4,000 minus 4x. We have to find our critical numbers. Now remember, our critical numbers are where the derivative is 0 or undefined. 4,000 minus 4x is never undefined, but we can set it equal to 0 and get x equal to 1,000. Now, even though we know that this is going to be a maximum value because we know how this function behaves, it's an upside down parabola, I am going to prove that it is a maximum by using the first derivative test. So I'm going to put 1,000 on my number line, and I'm going to look at the derivative before 1,000 and after 1,000. So if I put in, let's just say 500, my derivative at 500, so here's my derivative, I put 500 in here, I'm going to get 4,000 minus 2,000, which is 2,000, it's positive. So then I know before 1,000 that the area is going to keep increasing. As soon as we hit a width of 1,000 feet, then what's going to happen over here? Well, let's pick something to the right of 1,000. Let's just say 2,000, for example, anything to the right of 1,000. And if I put 2,000 in here, I'm going to get 8,000, so 4,000 minus 8,000 is going to be negative 4,000. The derivative is negative to the right of 1,000, so the area decreases after that. So we just use the first derivative test to prove that this is a maximum. We have a maximum at x equals 1,000. So the question says, let's go back and reread the question, make sure we answer what it's asking. It says, if the farmer does not fence along the river, what is the largest area that can be enclosed? Well, if x is, we know that 2x plus y equals 4,000, right? We know that the maximum happens when x is 1,000, so we plug that in, we get 2,000 plus y equals 4,000. So the length of the pen is going to be 2,000. So we have our pen here, a 1,000 foot wide by a 2,000, what was it, meter, big fence, right? It's going to give us the maximum area, and the maximum area is going to be the length times the width, which will be 1,000 times 2,000, which is 2 million. Now it's area, and it's meters times meters, so meters squared. And that would be my final answer. All right, let's look at another problem. Maximizing the volume. So often when we make boxes, we start with either a rectangular or square piece of material, we cut out the corners. So here we want to start with, it says from each corner of a square piece of sheet metal, so I have a square piece, so a square definitely has sides that are the same. The lengths of the sides are all the same. And we're going to remove squares and turn up the edges to form an open box, and we want to maximize the volume. So we're going to cut out little squares. And we're going to fold this guy up. So when we cut those squares out and we fold this guy up, oh, sorry. My cat just jumped on the table and shook the camera. Mookie. My daughter's cat, actually, let's see. All right, there we go. All right, so when we take this, it's going to turn into a box once we fold those sides up. So this is what we're looking for. And the height of the box right here is going to be determined by the little squares that we cut out. So this right here will correspond to that. All right, let's see what we know. In this case, we know that each side of the box is 18 centimeters, right? Because it's square, so all sides are 18 centimeters. And remove a small square. And we don't know how much we're removing, and it's a square, so we're going to cut out X and X here. All right, so now when we create our box, the height of the box is going to be X. And the width of the box is going to be, this is X, and this is X. And the width of the box is going to be the length of these little pieces in here. So if we take 18 centimeters and we cut X out of each corner, this is going to be 18 minus 2X. And that's also going to be the length of the box because we started with a square piece of material. So we want to maximize the volume of the box. Okay, so if we start with a square piece of sheet metal, 18 centimeters on each side, we cut out X, a square of side X from each corner, and this is the box that we'll produce, and the volume of this box will be the length times the width times the height. So here is what we want to maximize, the volume of the box. Now notice the volume was handed to us all in terms of just one variable X. So we don't need another equation. We don't have a constraint equation here. I guess we do have a constraint, I should say, because we know that X has to be greater than 9 centimeters, because if it's less than 9 centimeters, then we'll just obliterate our box totally. So we do have this constraint, but as far as rewriting the volume in terms of one variable, the way the information was presented to us, we have it all just handed to us. All right, so now here on how you take the derivative, I'm going to rewrite this as X times 18 minus 2X squared. Now you could distribute, you could do 18 minus 2X times 18 minus 2X and get a third degree, excuse me, a third degree expression, polynomial, and take the derivative. But I'm going to try to avoid doing all that extra algebra, and I'm going to take the derivative right from here by using both the product rule and the chain rule. So the next step is to take the derivative. I have X times 18 minus 2X squared, so the derivative of the first is 1 times 18 minus 2X squared plus the first times the derivative of the second. Now the derivative of quantity 18 minus 2X squared, well, I bring the power out front, leave what's inside alone, drop the power by 1 times the derivative of what's inside. So I use the chain rule to find the derivative of the second piece. So I'm just going to clean this up a little bit. 18 minus 2X squared, and then I have minus 2X times 2X, so I'm going to call that minus 4X squared times 18 minus 2X. Right, now we want to know where is this derivative either 0 or undefined. Again, this is just a polynomial. It's not undefined anywhere, so I'm just going to see where it equals 0. So again, you can distribute this out, but I'm going to use techniques that we did in the max-min section, and I'm going to notice that both of these terms here, we have this chunk of stuff minus this chunk of stuff, and both of these terms have an 18 minus 2x in them. So if you pull the 18 minus 2x out from each term, what's left here is we still have 118 minus 2x. Here we took out this entire 18 minus 2x, so it's going to be 18 minus 2x times 18 minus 2x times the remaining 18 minus 2x minus 4x squared. Ooh, oh no, I lost something. Sorry, hold on, go back pedal. This is not right. We don't want this x in here. Be careful, I made a mistake. Let's go back up here. When I took the derivative of the first and the derivative of the second, I made a mistake and I made my problem much more complicated. The derivative of the first is 1 times the plain old second plus the plain old first times the derivative of the second. When I took the derivative of the second, I brought the 2 out front, left what was inside alone, dropped the power by 1, and the derivative of what's inside is just -2, because the derivative of -2x is just -2, so not sure if you caught that. So we really don't have this power here. And then this is just going to be, when I pull out the 18 minus 2x, that's just going to be 4x, plain old 4x. Ooh, much easier. And that's going to be equal to 0, so I'm just going to clean this up. And now it's nicely factored for us. 18 minus 6x equals 0. So now we have to determine, whoops, hold on, my TV got really loud. It's Grey's Anatomy, so if you're hearing weird sounds, there we go. All right, there we go, much better, sorry. So where is this derivative equal to 0? Well, the first factor tells me the derivative is equal to 0 when x is 9, and the second one tells me that the derivative is 0 when x is equal to 3. So now a lot of times this is common sense. If we go up here and x is equal to 9, we'll completely eliminate the box. If we cut out corners of 9 by 9 corners, the width and the length would become 0. So my instinct is that we're going to cut out corners of size 3 by 3, but let's just confirm that 3 by 3 is a maximum for this function. So I'm going to put 3 on the number line. I'm going to put 9 on the number line, and I'm going to check how the derivative of the volume behaves before, between, and after. So it's the derivative of the volume that we're looking for. So here is the derivative of the volume. Actually, let's just write that right here. I'm going to write v prime is equal to 18 minus 2x times 18 minus 6x. So if I pick my favorite number to the left of 3, let's say 0, and I put 0 in here, I get 18 times 18. So it's going to be, my derivative is going to be positive. So my original function will be increasing to the right of 3. I pick my favorite number between 3 and 9. So like here I pick 0. I'm just going to say 5. If I put 5 in here, I get 18 minus 10, which is 8. And then 18 minus 30, which is -12, so positive times a negative, it's going to be negative. So the original function is decreasing. The volume decreases. Once we hit a corner of a 3 by 3 corner and we start cutting out bigger corners, our volume is going to start decreasing. And then after 9, well, after 9 it makes no sense because our box will disappear. So if the function increases then decreases, then we know that this is a max. We're going to get the max volume at 3 when we cut out corners of size 3. So therefore, we go back to our it says, what are the dimensions of the box with the largest volume? Well, x is going to be 3, so it's going to be a 3. If we put 3 in here, it's going to be 12 by 12. Therefore, x equals 3 implies each side's going to be 18 minus 2x, which will be 12. And the dimensions of the box with the largest volume, whoops, I combined words, with the largest will be a 12 centimeter by 12 centimeter by 3 centimeter box. Here we go. All right, let's keep playing along. I've got 2 more problems. The third one is minimizing cost. This is a problem that's very logical. If a manufacturer has some sort of product that they need to put into a container and they want to design the container in such a way that it uses the least amount of money but holds the right capacity of the liquid, let's say, then this is a perfect type of problem for that. So we need to produce a cylinder container like a can with a capacity of 100 centimeters cubed. The top and the bottom cost more than the sides do. So we want to know what are the dimensions of the can that we can produce that will cost the manufacturer the least amount of money. All right, so we have our can. So the top is that 5 cents? Right, per centimeter squared, and then the sides is 3 cents per centimeter squared, right? And we need to, we want to minimize the cost. Right, well, what's the cost of making a tin can? So when we have the cost and we're looking at the material to make the cost, we have to think that this is the surface area is what we're trying to minimize, because the smallest surface area will produce the cheapest can. Right, so I'm going to deconstruct this can, right? Oh, and the bottom, don't forget the bottom too. We have to put a bottom on our can. Is 5 cents. All right, so I'm going to deconstruct this can. I have the top, I have the bottom, and then I have the sides. But when we unroll a tin can, it's really just a rectangle. So we have the top, the bottom, and then the side, all around. All right, so we want to minimize the area. So the area of the top is pi r squared. The area of the bottom is pi r squared. And then, well, we have the height of the can, right? And then this is going to be the width of the can is the circumference, 2 pi r. So the area of the sides is going to be h times 2 pi r. So the top, the surface area of the top is pi r squared. The surface area of the bottom is also pi r squared, assuming that we have a can of radius r and height h. If we cut the can, make a slit in the can, and open it up, it gives us a rectangle of height h and length 2 pi r, which would be the circumference of the top and the bottom. So now the cost of the can, which we want to minimize, is, well, it's 5 cents for the top and the bottom. So it's going to be 0.05 times pi r squared plus another 5 cents for the bottom. And then this is going to cost us 3 cents. So it's 3 cents times h 2 pi r. All right, so a couple things to look at here. We have the cost. Our cost can be expressed in terms of the radius and the height, which is 2 variables. Now, like the last problem, if we didn't have a constraint, the cost of the cheapest can would obviously be a little itty bitty tiny, almost nothing can. But the problem is we have to put in 1,000 cubic centimeters. So that's going to be the constraint. Here's the cost, but our constraint, right? It needs to hold 1,000 cubic centimeters, right? So in other words, the volume, which is pi r squared times the height, has to equal 1,000. So this is a fixed equation that has a value. What we can do is we pick one of the variables and solve for it, and then we're going to plug it back in up here. So clearly h is the easier variable to solve for. So if pi r squared times h equals 1,000, then h is 1,000 all over pi r squared. So therefore my cost function is now 0.05 pi r squared plus 0.05 pi r squared plus 0.03 h. I'm going to replace with 1,000 pi over r squared times 2 pi r. So now we have our cost written exclusively in terms of the radius of the can. Right, let's clean this guy up. So my cost is, well, 0.05 pi r squared, 0.05 pi r squared is 0.1 pi r squared. Plus, well, this r cancels out with this r, those two pi's cancel out, 0.03 times that is going to give me 6, let me see, that's 0.06 times 1,000, so that's going to give me 60 over r. There we go. So that cleaned up nicely. So now in order to find the minimum value of this function, we're going to take the derivative, And we're going to see where it's either undefined or 0. So take the derivative, we can get 0.2 pi r. So this is, think of this as 60r to the negative 1 power minus 60r to the negative 2. Right, now we do have, this time we have a place where the derivative is undefined. So I'm going to clean this up a little bit. Let me rewrite this as 0.2 pi r minus 60 over r squared. So it's undefined when the radius equals 0. But that's nonsense in this case. We can't have a can with radius 0. So we're going to disregard that critical number, and we are just going to set it equal to 0. So let's set this equal to 0. I'll add the 60r over r squared to both sides. I'm gonna bring the r squared over to this side. I'm gonna multiply both sides by r squared, so we get r cubed equals 60. And then I'm gonna divide out the 0.02, so r cubed is equal to 60, 0.2 pi. And 60 divided by 0.02 is 300. This all comes down to 300, r cubed. So the radius cubed is 300 over pi. So to solve for r, we're going to cube root both sides. So the radius that's going to produce a can with the minimum cost is the cube root of 300 over pi. Not a nice number, but it is a number. So now we have to, I'm going to say that's about, if we pop this in our calculator, 4.6-ish. Right, so we're going to put this on a number line and we're going to confirm. 0 is also a critical number, but we know that 0 doesn't make sense in this problem, but I'll put it on the number line anyway. So 300 over pi, and let's check the derivative of the cost to the left and the right of this 4.6-ish number and see how the cost behaves. So here's the derivative of the cost, and I'm going to just put in, let's say 1, for example. So if I put in 1, my cost is going to be, well, 0.02 pi times 1 minus 60 over 1 is going to be 0.02 pi minus 60. 0.02 pi is a very small number, less than 1, so 1 minus 60 is going to be negative. So my cost is decreasing until it hits this number. Then I pick any number to the right of this number, and I'm going to pick like 100. If I put 100 in here, 60 over 100 is just 0.6, and this is going to be 300, it's going to be 60, so this is going to be much bigger than that number. It's going to be positive, and you can pop that in your calculator to confirm. So the function increases, so the function decreases, hits the cube root of 300 over pi, then it starts increasing, so that confirms that we have a minimum cost at a radius of the cube root of 300 over pi. All right, now we got to go back though and see what this question's asking us. What did the question say? It says find the dimensions that will minimize the company's cost to produce the container. So we have to go back. We have to look at our constraint, keeping in mind that we had, let's see right here, the volume, which was pi r squared times h, must equal 1,000. We found r to be the cube root of 300 over pi. So not a nice number, but we have pi times the cube root of 300 over pi squared times h is equal to 1,000. So h is going to be, we're just going to take this whole mess, and I'm not going to worry about simplifying it, pi cube root 300 over pi squared. So therefore, the can, or the container, which will minimize cost, will have radius r equals the cube root of 300 over pi centimeters in height. equal to 1,000 over pi times the cube root of 300. I'm sure this can be broken down or simplified a little bit, but we are leaving it right like that, centimeters. Woohoo! All right, it's gonna be a really long video. One more, kids, okay? Let's just set up this last problem. Lastly, a rectangular is inscribed in a semicircle of radius 2. Find the dimension of the rectangle that has the maximum area. So I have a semicircle. I know the radius is 2. I'll put there in a moment. Now rectangle. Right here. All right. So this gets a little tricky because how is the radius going to be helpful? If we draw all different radii from here, the radius is always 2, but the one that makes the most sense is this guy right here. That's what's going to help us in this problem. So we have a rectangle. Here's x, here's y, right? And then we have our radius, which we know is 2. So I'm actually just going to write that to be 2. So that actually, this line is going to be our constraint. So what I'm going to focus on here is, remember, we want to maximize the area of this rectangle, right? And this is right in the center of the rectangle. So if this has length x, this has length x over 2, and this has length x over 2, and this side is y. So we want to maximize the area of this rectangle. So the area is just x times y. But we have 2 variables here, so what we need to do is use the given information to solve for one variable in terms of the other. But let's focus on right here. If you notice, what we have here is a right triangle. So our constraint, because we're stuck inside a circle of radius 2, x over 2 squared plus y squared equals 2 squared. So in other words, we have to solve for one of these. X squared over 4 plus y squared equals 4. I'm going to solve for y. Y squared equals 4 minus x squared over 4. So y is equal to the square root of 4 minus x squared over 4. Now we're going to plug that back into our area. So our area is x times y, or x times the square root of 4 minus, I'm actually going to write 1/4 x squared. It's not as painful looking. And that's what we need to maximize. So when I take derivatives, I like to turn radicals into fractional powers. All right, so we're going to take the derivative and we're going to set it equal to 0, or see where it's undefined. All right, so let's go, guys. Getting lots of practice with our derivatives here. So the derivative of the area, I'm going to use the product rule. It's the derivative of the first times the second minus the first times the derivative of the second. Bring the power out front. Leave what's inside alone. Drop the power by 1 times the derivative of what's inside, which would be, bring this power out front. It's going to be -1/2 x. Woo! All right, let's clean this up. This is, I'm going to turn this back into square roots. 4 minus 1/4 x squared minus, we have x squared here, right? So that's x squared on top. And we have 2 times 2, which is 4, and then we have this new radical down here. All right. So now we have to decide where this is 0 and undefined. Well, it's undefined when this denominator is 0. So let's take a look at when this is 0 to see if the undefined case makes sense. So this cannot equal 0. So we're going to have x squared can't equal 16, right? So 4 equals 1/4 x squared. Multiply both sides by 4, we get 16x squared, and x equals 4. Oh, I guess that does make sense. We could have x equals 4, right? So x could be 4. The radius is 2. That it makes sense. X might be 4. So we're good with that. And now we have to see where this equals 0. When does 4 minus 1/4 x squared minus x squared all over the square root of 4 minus 1/4 x squared equals 0? Not as horrible as it looks. This comes with practice. So I'm going to bring this over to this side. 4 minus 1/4 x squared equals x squared all over 4 minus 1/4 x squared. Now I'm going to multiply both sides by 4 times 4 minus 1/4 x squared, the square root, to get rid of the fraction. So 4, the square root of something times itself, is just going to be 4 times 4 minus 1/4 x squared. The radicals cancel each other out. Equals x squared. This actually is not turning out to be all that horrible. So I get 16 minus x squared equals x squared. Add x squared to both sides. 16 equals 2x squareds. Divide by 2. 8 equals x squared. X is equal to the positive negative square root of 8. We're going to exclude the negative because that can't be the side of a rectangle. So x is equal to 2 square root of 2. So therefore my critical numbers are 4 and 2 square root of 2. So 2 square root of 2, 4. We're going to look at how the derivative behaves before, between, and after. So let me write this derivative down again. Yikes. 4 minus 1/4 x squared minus x squared all over 4 minus 1/4 x squared. All right, now I'm getting really, really long on time here, so I'm actually going to let you pop these numbers in. I pick any number to the left, and I'm going to get a positive value. So if I just plug in 0 here for x and 0 here for x, you can see that this term turns into 0. Here, this just becomes a square root of 4, which is 2, and it's positive. If I pick any number to the between 2 square root of 2 and 4, like 3, for example. No, actually, that might be too big, right? Because what's 2 square root of 2? 2 square root of 2 is 2.8. So 2 square root of 2 is 2.8. So we can put in 3. And if you put 3 in here and 3 in here, I promise you that your output's going to be negative. And then we can't put anything bigger than 4 in because that's outside of our domain. It will produce a negative under the radical. So the area increases until we get a side of length 2 square root of 2, and then it decreases. So therefore, this is definitely a max at x equals 2 square root of 2. All right, so let's just go now answer the question and finish this section up. I was going to take like 4 years for this to download. Find the dimensions of the rectangle that has the maximum area. So if x is equal to 2 square root of 2, and then the constraint was x over 2 squared plus y squared must equal 4. So if we put 2 square root of 2 in here, so this is 2 square root of 2 over 2 is just going to be the square root of 2 squared plus y squared equals 4. So then we're going to get 2 plus y squared equals 4. Y squared equals 2. So y also equals the square root of 2. So therefore, the dimensions of the rectangle that would produce the largest area is square root of 2. It's actually a square. Does it give me units? Nope, that's all we know. All right, guys, I know that was really long. Thank you for your patience. Hopefully you made it to the end. To do, read 4.7 in Stewart. Exercises 1 to 15 odd, 19, 21, and 25. There's gazillions of problems on the internet. Let's see, 2.4, 4.7 optimization. Hold on, let me see. Need to do in Stewart optimization. I think this might be 4.7 also in XYZ, but go to your Blackboard announcements and you can confirm. So corresponding XYZ homework. Check Blackboard for due dates. I started saying, sorry, I interrupted myself. There's zillions of optimization problems on the internet. So if you just Google optimization examples, calculus optimization problems, you will find tons and tons of problems with examples. So feel free to explore that too. And don't forget to zoom in if you have questions or concerns or you want to talk about anything. All right. Hope everybody's well. Bye.